Welcome to Summative Assessment number 1 for our midterms. Today we are going to use OrCAD Pspice to solve our problem. Our problem today is a current of 5 sine 2 pi 60t A enters an element. Sketch the instantaneous power and determine the average power absorbed by the load element when the element is a 5 ohm resistor, a 10 millihenry inductor, and a 12V source current into the positive terminal. Later, I will also show you the calculated theoretical value so that we can compare our simulation results. For our first circuit, we are going to use a current AC source. So let's search current sine. We will use a transient sine current source, I sine. Then let's maximize. Then let's place a resistor. 8, then ground, 0 cap C. Then based from the given values, the amplitude of our current source is 5. Then the frequency is 60 Hz. The offset is 0. Let's change the value of the resistor to 5 ohms. Now let's simulate our data. Let's go to new simulation profile. Let's name this sum A resistor. Create. For the simulation settings, we are going to use time domain transients as our analysis type, and our runtime time seconds is 16.67 milliseconds or 0.01667. Then click apply. Then run Pspice. Let's go to trace. Based from the given problem, we are going to determine the instantaneous power and the average power. So in the trace expression, we are going to type W R1 and AVG average power, then WR1. In the simulation, the green waveform is the instantaneous power and the red waveform is the average power. To measure the peak instantaneous power, let's click on the waveform, then right click, cursor on, let's go to its peak value. Using the cursor, we recorded an instantaneous power of 124.937 watts. To move the cursor to measure the average, click here. For the average power, we will measure it on the stop time. In the end of the waveform, the value that we got is 62.939 watts. So this is the AC waveforms of our instantaneous power and average power when the current source goes to a load element such as the resistor. To verify if our computed values are correct, we will compare it to our computed theoretical values. Based from our calculation, we calculated an instantaneous power of 125 watts and an average power of 61.41 watts. Based from the measured and calculated values, we can observe that there is a small percentage difference between each other. To show you how we calculated the theoretical values, for this part we are given a value of 5 ohms and a current value of 5 sine 2 pi 60A. The voltage across the resistor is VR is equals to ITR. 5 sine 2 pi 60t times 5 ohms is equals to 25 sine 2 pi 60t V. To compute for our instantaneous power, VR times IT, 25 sine 2 pi 60t V times 5 sine 2 pi 60t TA, it is equal to 125 sine squared 2 pi 60t watts. Based from the calculation, the peak instantaneous power is 125 watts, which is near to our measured value in the simulation. For the formula for average power, it is equals to 1 over T, PT or instantaneous power dt from 0 to T. Then here, substitute our values. We use a half angle so it will be easier to integrate the expression. Using the half angle, the instantaneous power was converted to 1 minus cosine 2 pi 60t over 2. Since 125 is constant, we separated it from the integral expression. After it was integrated, it resulted to t minus sine 2 pi 60t over 2 pi 60 from 0 to 16.7 milliseconds. From there, we calculated an average power of 61.41 watts. Now, let's change this element to an inductor. So, delete. Then, let's place an inductor. There. 8. Then, the value of our inductor is 10 millihenries. Then, run Pspice. Then trace. For the trace expression, let's type W L1. Then average AVG W L1. Based on the simulation result, we can say that the AC waveforms in an inductor circuit is different with the waveforms in a resistor circuit. The green waveform is our instantaneous power and the red waveform is our average power. Now let's measure the peak value in the instantaneous power. Right click, cursor on. For our instantaneous power, we recorded a value of 47.215 watts. We can also determine the peak-to-peak instantaneous power. Let's go to trace, add trace, then negative WL1. With the cursor at the positive instantaneous power, we can see that the peak-to-peak instantaneous power is 94.49 watts here. Later, I will also show you why did we get the peak-to-peak instantaneous power value in the simulation and the peak value of the instantaneous power. To measure the average power, click here. We will measure the average power at the end of its waveform. For the average power, we recorded the value of 60.760 milliwatts. So that is 0.06. Meaning the average power is too small. We can round it off to 0 watts. I will show you the calculated value so that we can compare our measured values from the simulation. In the simulation, we recorded an instantaneous power of 47.215 watts, and our calculated value is 47.12 watts. Our measured average power from the simulation is 0.061 watts, and our calculated value is 0 watts. From the comparison, we can say that there is a small percentage difference between the measured and calculated values. To show you how we calculated the instantaneous power and average power, the formula for the instantaneous power is P is equals to VL times the current. The voltage across the inductor is L di over dt. We are given a value of 10 millihenry for an inductor and current source of 5 sin 2 pi 60t. Substituting our values from our formula, we came up with an answer of 94.24 sin squared 2 pi 60t as our total instantaneous power, or our peak-to-peak power. The instantaneous power waveform in an inductor circuit has a power consumed and power return. The positive cycle is the power consumed and the negative cycle is the power return. From the total instantaneous power, 94.24 sin squared 2 pi 60t, we use a double angle wherein sin squared theta is equal to sin theta cos theta. We came up with a value of power consumed and power return of 47.12 sin 2 pi 60t and cos 2 pi 60t. For the average power, the formula is 1 over t, integral of pt or instantaneous power dt from 0 to t. So substituting our value of power consumed and power return, 47.12 sin 2 pi 60t cos 2 pi 60t dt. To integrate this expression, let's separate the constant of 47.12, wherein sin s cos x is equal to 1/2 sin 2x. From the sin 2x, our 2 pi 60t became 4 pi 60t. Then we separate again the constant, 1/2. Then we integrate sin 4 pi 60t. We came up with negative cosine 4 pi 60t over 4 pi 60. Then as we evaluate the expression, we came up with an answer of 0.04498 watts, which we rounded off to a value of 0 watts. So in an inductor circuit, the average power is 0 watts. To recall our measured and calculated values, we can say that there is a small percentage difference between our measured and calculated values. Now, for the third part, we will replace this inductor with a 12V source. Go to place, Pspice component, source, voltage, DC, there. From there, we are given a value of 12V DC, so let's change this to 12. There, edit simulation profile, simulation settings, 16.67 millisecond for our runtime time and analysis type, also time domain. Okay, then run Pspice. Let's go to trace, add trace, then WV1 and AVG WV1. Based from the simulation, both power waveforms started in its negative cycle. To measure the instantaneous power, let's go to cursor on, then let's move it in our waveform where it is in at its peak value. There. From there, the peak instantaneous power, we recorded the value of 59.990 watts. To measure the average power, let's click here, and we will measure the average power in the stop time at the end of its waveform. And for the average power, we recorded the value of negative 9.3193 milliwatts. To verify if our measured values are correct, we will also compare it to our calculated values. Here, in comparison with the calculated values, we measured our instantaneous power of 59.990 watts. Our calculated value is 60 watts. We were able to measure the average power wherein we rounded off its value to 0.001 watts. Our calculated value is 0 watts. From there, we can say that there is a small percentage difference between our measured values and calculated values. I will also show you how we calculated the theoretical values. From this circuit, we are given a value of 12 volts as our DC voltage and the current value of 5 sin 2 pi 60 amperes. For the instantaneous power, the formula is VDC times IT. So 12V times 5 sine 2 pi 60A is equals to 60 sine 2 pi 60W. Meaning the peak instantaneous power is 60 watts. For the average current, the formula is 1 over T, integral of IT dt from 0 to T. Then we substitute the value of the current, 5 sine 2 pi 60T dt. In the integration, we separated the constant 5. Then we integrate sine 2 pi 60T dt. After the integration, it became negative cosine 2 pi 60T over 2 pi 60 from 0 to 16.67 millisecond. From there, we evaluate and came up to compute for the average power. It is equals to P_av equals VDC times I_av. Then 12V times 0A is equals to 0 watts. To recall, our measured values has a small percentage difference between our calculated values. From there, we can conclude that from the 3 simulations that we have done, OrCAD Pspice simulation offers accurate results because if we are to compare our calculated values and measured values from the 3 trials, there is a small percentage difference or discrepancy from our results.